All right, today we are diving into a really fascinating new paper out of the Chinese Academy of Sciences that might just completely reshape how we think about AI. The model is called SpikingBrain, and it's inspired by, you guessed it, the human brain, and it tackles one of the biggest problems in AI head-on. Let's get right into it. But first, let me just ask you this. What if we could run our most powerful AI models using the same amount of energy it takes to power a single 20-watt light bulb? I know, it sounds like something straight out of science fiction, right? But that is exactly the kind of radical efficiency we're talking about today. But before we can get to the really cool stuff, the breakthrough, we kind of need to set the stage. To really appreciate how revolutionary SpikingBrain is, we first have to understand the massive, and I mean massive, growing pains that the entire field of AI is facing right now. So what do you think is the single biggest weakness of these incredible AI models we use every single day? It's not their intelligence, it's not their creativity. Nope, it's their staggering inefficiency. And this all comes down to a fundamental bottleneck baked right into their architecture. And the culprit has this kind of scary-sounding name, quadratic complexity. But in simple terms, here's what it means for the transformer models that power pretty much everything. The longer the text you feed it, the cost to compute it doesn't just go up, it explodes. Doubling the length of your text doesn't double the cost, it quadruples it. And this makes processing really long things like analyzing an entire novel or a whole strand of DNA insanely slow and expensive. So how do we fix a problem like that? Well, the researchers behind SpikingBrain looked to the most efficient and complex computer we've ever known, the human brain. Turns out, nature kind of solved this problem for us billions of years ago. And this is where the difference just becomes so stark. Mainstream AI gets smarter through what the paper calls exogenous complexity, which is basically a fancy way of saying brute force. We just throw more data and more computing power at the problem, and these data centers consume megawatts of energy. The brain, though, it uses endogenous complexity. Its intelligence comes from its incredible internal structure. It's an event-driven system that just sips power, using only about 20 watts. It's just a completely different philosophy. Okay, so this brings us to the star of the show. How exactly does SpikingBrain copy from the brain's playbook to build a way more efficient AI? Let's break down how it actually works under the hood. SpikingBrain is really built on three key innovations. First, there's hybrid efficient attention, which finally gets rid of that crazy expensive quadratic complexity we were just talking about. Second, it uses a mixture of experts, or MO. Now, you can think of this like having a whole team of specialists. Instead of the entire team working on every single problem, only the one expert who's needed for the job gets activated. It saves a ton of energy. And third, the real game changer, spike encoding. So here's how this spike encoding thing works, and it's actually pretty intuitive. Instead of every single neuron constantly crunching numbers all the time, SpikingBrain's neurons act more like a bucket filling up with water. A neuron just sits there quietly accumulating information until it hits a certain threshold. And then, bam. It fires off one single, super efficient pulse of information, a spike, and then it just goes quiet again. It only works when it absolutely has to, which is the secret to its incredible efficiency. Okay, so we've covered the theory. Now, let's get to the results, and honestly, the numbers here are pretty mind-blowing. And these come straight from their research paper, which you can find on Archive if you want to check it out yourself. Let's just start with this number, over 100 times faster. That's a conservative estimate of SpikingBrain's speed up when you're processing a super long sequence. We're talking 4 million tokens compared to a standard model. This isn't just a small improvement, it's a whole different league. And this chart really just says it all. This shows the time to first token, which is basically how long you have to wait for the AI to start talking back to you. For a normal model, that wait time just explodes as the text gets longer. But look at SpikingBrain. That line is almost flat. At 1 million tokens, it's already more than 26 times faster. At 4 million tokens, where a standard model can't even run, SpikingBrain is projected to be over 100 times faster. It's almost instantaneous. And here is the number behind all that power efficiency, 69.15%. This is the sparsity that the model achieves. And what that means is, at any given moment, because of that whole spike and rest thing we talked about, over 2/3 of the entire network is silent. It's just resting, not using any power. That is how you get down to that 20-watt light bulb level of efficiency. So you're probably asking the most important question of all right now. Is it still smart? Right? Does all this amazing efficiency come at the cost of performance? And the answer, incredibly, is no, not at all. If you look at the MMLU benchmark scores, which are a big test of reasoning ability, the 76 billion parameter SpikingBrain model actually performs right on par with, and in some cases even better than, much larger models like Llama 2 and Gemma 2, all while activating way fewer of its internal parameters. So what does all of this actually mean for us? This isn't just some clever experiment in a lab. This research is pointing toward a fundamental shift in how we build and use AI, and it has some profound real-world implications. Yeah, the real-world impact here could be huge. For science, it means we can finally analyze massive data sets, like the entire human genome, super efficiently. For you and me, it means having powerful AI running right on our phones without completely draining the battery in 5 minutes. This research also proved this can all be done on non-NVIDIA hardware, which helps break open the whole ecosystem. And maybe the most exciting part, it paves the way for a totally new class of computer chips, neuromorphic chips, literally designed to think like a brain. As the researchers themselves put it right in their paper, this isn't just about making today's models a little bit faster. It's about showing a whole new path forward, a path that's inspired by biology to create the next generation of AI that's truly efficient and can actually scale. Which really just leaves us with one final, kind of provocative thought. For decades, we've tried to build intelligent machines out of silicon and pure brute force. But maybe the true path to artificial general intelligence has been inside our own heads this whole time. Is the future of AI not just digital, but biological?